Hello and welcome to the content example walkthrough. Today we're going to be going through the Niagara Particles Hall. If you have trouble getting here, once you open the content examples, you can open the content drawer by clicking on this. And under this maps folder, we have Niagara Particles, Niagara underscore particles, which is the hall that we're talking about today. And let's dive right into it. In our first exhibit, it's just talking about what actually are Niagara systems. So, Niagara is the visual effects and particle system that's used in Unreal Engine. So, everything from explosions to smoke and sparks that fly when two swords hit each other to a ton of other things are done with Niagara. Um, we can come to the details here and double click on this preview to open the actual Niagara system. The Epic has left us tons of lovely notes. If you are confused about certain parts or just want a little bit more in depth or anything like that, I highly recommend downloading this and reading these for yourself. And you can always read along with me and pause the video wherever you need to get some refreshers. So each system, and actually I'm just going to pull these up so it's a little bit less cluttered, has two main things: a system tab and a emitter. The system is uh, for right now, you can think of it as just the container. Really don't have to set anything up in this unless you're going into more advanced things. It's just the module that's needed to actually have a system, but all of the real magic happens in the emitters. The emitter is exactly what it sounds like. It's what emits the particles uh, and does things to the particles. So, uh, in each emitter, we have these, and I'm just going to collapse these. We have these sections, which are all called stages. Uh, it's very similar to blueprinting, if you've done that yet, where you have a on begin play and you have a on tick. Spawn is the on begin play, and then update is on tick. So spawn happens when it's created, and then update happens every frame that exists, so long as that it exists. And you can see here we have these both for the emitter and the particles that are created in this emitter. So emitter spawn is actually completely empty in this, and then we have emitter update. And you can see here that we have two modules. Modules are what you add to the stages to actually give them some functionality. First one here doesn't really do anything beyond it's just saying that it belongs to this system. And then we have our spawn rate. So this is the first thing we can actually interact with. So this is saying, and the tooltips for these are very good. So if you're ever stuck, I recommend doing this. You can just hover over it and it tells us spawns particles continuously at a particular rate. That's simple. So we can reduce this down to once a second. So now we're just bubbling particles occasionally. We can crank it up to 10, and now it's a nice stream, all good stuff. So next we have particle spawn. So we know that this is only going to happen the first frame that each of these little particles exists. So what we're doing in here, so we have initialize, we are setting the lifetime of the particle. How long should it live for? Right now that's set to 4 seconds. And then we're setting a color so we can make all of our particles red if we want to. And we're setting those right when it spawns. The other thing we set here is the sprite size. And then the only other thing that we do on spawn is we give them a velocity. So in this case, they have a velocity of 40 in the z direction, which is going straight up. So I can change this to 40 here and then set z back to 0. And now they're going off to the left, just like that. So then in the next step, we have the particle update. So what should we do to the particles every single frame? So first one, particle state, we're just saying when your lifetime is over, delete the particle. Then we are actually scaling the sprites over time. So we can see that it kind of looks like a little bit of sine wave as far as their size. And that's determined by this scale here. So, like, I can take this and make this a much sharper spike, dragging these keys around. And if I leave it alone, we can see that now that that's the case, these have a much sharper spike. I could also do the opposite. I could move these out and delete this. And now it's a just kind of grows and then shrinks a little bit, right? Um, Scale color. We're not actually scaling the RGB value of this here. We're scaling the alpha. And this is where we'll talk about our first thing, where you don't always have to have uh, just set values like this one. And this is what we're doing with the alpha, where we're saying we want you to determine a value to put the alpha at based off of a curve. So that's what float from curve means. And then in the curve, when we add that, we get this curve editor that we can use to determine it. So you can actually see the particles are kind of fading in, and then they're fully opaque, and then they fade out again, which works in line with this. So, like, if I bring this up here, it'll change it a bit so we can actually see that instead of fading out, they actually just shrink and die. And we're talking about fading out in opacity. If we actually do the same thing to our size without a crazy tangent, we should just see them pop out of existence. Yep. So now the particles just stop existing because we're not fading out of like we were in this state. We're just fully opaque until they die. So the only other thing that's in here is the solve forces. Anytime that you have any kind of velocity, like we are giving them when they spawn, you have to have a solver. This is how particle systems, what it's talking about is it's solving for all of the forces in the emitter every single frame. So if I turn this off, we can actually see that they spawn. And even though we're telling it you have a velocity, they're not going anywhere. Thankfully, Niagara's quite smart, and it will tell us once we turn that off, we get this big red dot here. It'll say one error. And then if we go to we click on it, it'll take us to the error and we'll say something is missing. So it's telling us we have to enable a solve forces and velocity, which it is dependent on. So I can turn this module back on, and that error goes away, and our particles start floating to the left again. So lovely. The last thing in the stack is the renderer. So all of these particles are not what we're seeing. They're just being fed into the actual render. So sprite renderer, it's dead simple. All it is a 2D image. You can give it other materials, so it's not just these little willow wispy blobs. We can change that into other things. So if we go to the next thing down the line, we're actually talking about the other type of render that we can have, which in this case is sprites. So, or meshes, I'm sorry. Uh, you can absolutely have other meshes. So in this case, at the very bottom, the only difference is we have this mesh renderer and we're feeding it this mesh. So I can change this to be, a bunch of paper lanterns, right? And if I actually make the spawn rate lower, it'll be a little bit more clear. But so we can be rendering whatever we want to represent our particles, right? The other thing you'll notice in this is that it also added some rotation. So we don't actually have to add rotational at the particle spawn. That's added here. So update mesh orientation, and then we can see it's set to rotation rate. So in this module, we have the rotation rate. It's set to rotation rate. We have other options here, but we can say this is the vector that I want you to rotate around, and this is how quickly. So if we change this to 10, they're going to spin much faster. We can also go down to 0.1, and it's a nice, barely rotating, but they are rotating kind of speed. Yeah. The next exhibit we have is talking about the different types of emitters. There are two main types, namely CPU emitters and GPU emitters. They're pretty close, but there are a couple of key differences. The rule of thumb I like to go by is that the GPU emitters can handle many more particles. That's what GPUs are good at. That's what they're designed to do. So you can have tens of thousands, hundreds of thousands, even if you uh, spend a lot of money of particles in your simulations. And then you have CPU emitters, which can't handle nearly as many particles, but the particles can do more advanced things. A couple examples of that are you can have collisions with characters, or you can actually uh, call events from particles on CPU renderers, on CPU emitters. And yeah, so some more advanced stuff, but rule of thumb is if you can make it work on a GPU emitter, that's better because that's what they're designed to do, handle tons and tons of particles. Oh, before I go away from this, actually, the way that's set is here. So at the very top of the emitter, we have the properties. And you can see right here it says GPU. Sim target is what it's talking about, and you just have the two options: CPU or GPU. Next, we have sprite facing. So this is talking a bit more about the actual sprite renderer. Sprite renderers are actually just flat 2D images. You can, by their default behavior, and we can actually change this here, they have something called their facing mode, and it's basically saying what way should that image face during a frame. So if I change it back from what they have to what it is normally, now all of the sprites are facing the camera, and they're facing the camera every single frame. So it's actually impossible to see the edge because they will always be facing the camera. But what this particular exhibit is showing off is that you can override it with a custom facing vector and tell it to do different things. So in this case, they look like they're on the surface of a bubble, is kind of how I think about it. And the way that you can achieve that is that you want to tell all of the sprites to face away from the center of the emitter. The way that is done is that we are given a sprite facing an alignment. So what this is doing is it's just one little bit of vector math where we're taking the current position of a particle, and then we're subtracting the position of the simulation. So particle's position minus the simulation position. And if you remember from your vector math, if we have a point A right here and a point B in the middle, if we take A minus B, it's going to give us a vector that points to the right towards the other vector. So A minus B makes a vector that is pointing from B to A. I know it's a little flipped, but I always just flop them back and forth until I get what I'm looking for. This also brings up a good point of what are these actual values that we're using, and those are the parameters that are available to us. So over in this tab, we have all of the parameters. We have system attributes. We also have emitter attributes, and then particle attributes, and we have these nice color coded tags so that we can tell the difference. And so if we read what this is accessing for, so it's reading the particle's position, so that would be particle's position. So, and if we hover over it, it tells us the position of the particle. And then we have the emitter simulation position. So that would be up here in emitter. Oh, and it tells us it's engine actually. So that will be engine provided. So it's engine emitter simulation position. Yeah, that's what it's doing. And then the other thing that's important, so we know that sprite renderer down here is using this custom facing vector. And if we hover over this, it'll tell us it's the sprite billboard faces towards the particles dot sprite facing vector attribute. So we need to somehow assign this value to that. So it tells us particles dot sprite facing is automatically applied by this sprite facing and alignment. And we can see that if we go into it, it is going to set stack context sprite alignment. So that's how that takes care of it. I don't need to talk about this yet. So that is how this emitter works. Okay, so moving on. The next section is talking about blending attributes. So if we open this emitter up, the attribute that's being blended here is the color. The way that's being done is in here, we have on every frame on update, we are changing the color of the particle. And so we're saying we want to start at red and go to blue. And the way that we want to lerp is using this, this value. Lerping is linear interpolation. It's a type of blending, but it's real simple. It just means going between two different points. And we can actually count colors as points because colors are no more than a vector 4 with 4 values, right? So, like if I change this to yellow, it will start as red in the center, go through orange, and then turn into yellow. And then they'll actually go back as they get closer to the center. So, how are we actually creating this normalized distance from center? So, um, it has this big gray or purple transient tab, and we can see here that we have another module called set and then the name of that variable. So we know that this is where it's getting set and where it's getting the information from. And what it's using to set this is something called a normalized distance range. Basically, what we're saying is that you have a start position, which is the particle's current position for this frame. And then you have a end position, and then that is going to be just the position of the owner, which is this emitter. And we're saying based on how far away are you from the engine position on a scale of 0 to 150. And then so that gives a normalized value, which is just a value between 0 and 1. And we're using that to lerp between red and orange, and red and yellow in this case. Yeah. Next, we have beam renderers. So they call it static beams. What this actually is ribbon renderers. And what ribbon renderers do is they draw a line through a set of points. So in this case, it's excuse me, it's spawning a bunch of particles in a line at a random direction, and then drawing both a ribbon through it and then drawing all the particles. So like if it's probably hard to see, but there are all of the little dots that are the particles in here. If I turn off the sprite renderer, we can just have the ribbon renderer, and then we can also do the opposite of that, just have the sprites. The only real difference with a ribbon renderer is that the order in which your particles have IDs in to tell it, I want to draw from this point to this point to this point, and basically telling it the order in which to connect the dots, right? So in this case, we obviously want it to go down the line as we're spawning. And it tells us over here that it does this using something called the ribbon ID. So this is done with some modules they already have set up for us called beam emitter setup. So the beam is actually the way to get all the particles into a line. And so we're saying we want you to always start the beam at the center of the simulation. And then we want the beam to point in a random direction that is between 220 and 340 units long, right? Then we burst, spawn burst a bunch of particles to fill up that beam. And then we actually have to spawn the beam. You actually don't need to, it's empty. You don't actually need to enter any information here. Uh, and then we have some other things that we can use to affect it. So we have some things like the beam width. So again, this is just another curve editor. We could make it look kind of like a dagger if we bring this up and then increase this scale to like 10. So yeah, now this beam is following half of this curve because we're talking about the width. So it's mirrored from on each side of the beam. So yeah. Next, we have another example of beams where you can actually have beams that will respond to individual points. So in this case, I can move the emitter around, and the point that it's connected to in the world doesn't actually change. The way that this is done is that in our beam emitter setup, we can actually give it a beam end position. So we're giving it this vector, and we're telling it it's an absolute, which means that it's not dependent on where the emitter is. And that's why we can move this around, because it's just saying it's this world position right here. So if I pull this off to the side, I can probably take this and move it up 50 units, and it will be in that same position in the world. So, yeah, we're actually defining it as a world position because we're saying it's absolute. So, yeah. Next, we're going to talk. We have multiple renderers. So, this is basically just showing off that you're not limited to only one render. In this case, we have all three types of renders that we've encountered so far. So we have just our sprites making little fuzzballs. We have meshes, so that's adding arrows to those fuzzballs. And then a ribbon renderer, which is connecting those particles together. Um, yeah, and we don't really need anything else for this. Yeah. You can have as many renders as you want. Obviously, it costs some performance, but yeah. So getting into a little bit more advanced. Next, we're going to talk about location emitters. So in this emitter, in this system, we can actually see that we have for the first time more than one emitter. So uh, just a side note, you can actually disable emitters in while you're previewing them. So if I turn these two off, we can see that this emitter is pretty dead simple. All it's doing is creating little fuzzballs. Uh, but the important thing is that down here in particle update, we are doing something with a module called generate location event. It's exactly what it sounds like. All it's doing is saying every single frame, I want something to happen at this location. The way it's doing that, it will create these location events, and it's saying I want something to happen at this location, and then we can create other emitters that will listen for those types of events and do things when they hear them. So in this case, we'll actually start with the right one. So in this case, it's saying uh, I want to spawn these little sparkler trails kind of behind each of these emitters, behind each of these particles that this first emitter is creating. So the way that that is done is that we need a separate stage called an event handler. And if we come to stage, there's actually only two types. We have the generic simulations and then event handlers. So we create an event handler. Um, it comes with this event handler properties. You almost never have to touch this. And then we need to tell it what type of event we want to listen for. So in this case, we are creating location events. So we give it a receive location events. And then in this receive location events, we have all of these options. These are all of the bits of information or the parameters that that generate location event is giving when it creates that event. So we have its position, its velocity, acceleration, all this stuff. And then for each of these, we have two options. We can either apply it or we can output it. Apply is exactly what it sounds like. We're saying we want to match the position of the particles that this makes to the positions of this one. So apply means match, and then output means save for later use. You don't have to use it, but it basically means no, I don't want to apply it, save it for later use. So in this case, we are applying the position, the acceleration, and then a couple other IDs that are actually probably not even needed. So the main one with this is that we are saving the position. So if I turn off the apply output, you can see that they're no longer following the points because they're not being told to follow their position. They're just starting at the spawn and staying there. And if I turn this back on, they're now applying these particles' positions to themselves and they're listening to it. The other thing that, this ribbon render is pretty darn similar. So, same thing, we have an event handler and a receive location event. And it's the same idea. We're applying the position to it. If we turn off this apply, ribbons actually start rendering because they're starting the ribbon and ending the ribbon at the origins. They have a length of 0, so they just don't exist. They don't have an actual length. So, um, yeah, that is how location events work. Next, we have expressions. Pretty simple, but very powerful. You can write code in any entry, any text box in Niagara. This is actually an Unreal thing. You can do this with most Unreal sections. So, like, if for some reason I wanted to, I couldn't figure out what 5,000 divided by 30 is, I can do 5,000 divided by 30 and hit enter, and it will compute that for you. But as you can see down here, if we can actually put in parameters from our Niagara system as expressions in any code, and it will change it to this expression code here, and it'll tell you it's now a custom expression. So we can do things like take the emitter age, multiply it by a sine multiplied by 56, or we can get random floats for the direction that we want these to face, or all sorts of stuff. So very, very powerful. It can sometimes be faster than adding lots of little modules. You can get it if you can just get the code done in one expression bar. So yeah, very neat. Occasionally useful. Next, we can talk about collisions. So this has 3 colliders in it, and I'm actually going to turn off the first 2. So if we come out, turn those off when we come out here, we can see that they're just colliding with the floor. So instead of like these particles over here that don't have collisions enabled, which are just passing through the floor, they will bounce, roll along it, all that stuff. It's pretty darn simple. That is done with a collision module. So there's a ton of settings, but they're pretty self-explanatory, and for the most part, you can leave them at their defaults. You can do things with friction, enabling rest, all that good stuff. Next, we have, and then I'm going to turn these 2 back on because this is going to talk about one of the other type of events we have, which are collision events. So they're pretty darn similar to location events, but they just happen whenever a collision occurs. So the way this is using it is it's making it so these green particles, when they hit the ground, they should release all of these spark particles, right? So every time that the big green particle collides with the ground, it creates an event and it spawns these little spark particles on the ground. And that is what this one's doing. And it's the same idea, but instead we're using a receive collision event, and we can get all of the information that we want from these. And these will spawn every time those collision events The next thing we can do is we can actually, instead of just spawning particles willy nilly in the air randomly, we can actually sample meshes. There's a lot of things you can do with this. I've seen people make it so that, moss or little mushrooms grow on the surface of things if they get wet over time. The sky is the limit for these. And it's pretty darn simple. It's a single module here, so it's static mesh location. So this is happening when we spawn the particle. And instead of declaring a set position, so our position mode is unset, and then we're setting it down here. So we're feeding it in a static mesh. So if we come to here, we have user static mesh sampler. So if we go to user exposed, and this, we can see where this is actually being used. And we can see this up here. Actually, it might be oh, you can see it right here. So when you bring these Niagara things into the world, you can say, I want you to be sampling this actor, static mesh, right? So uh, yeah, so it's taking the static mesh in. We have a couple different sampling types of triangles, sockets, or verts. And then a couple settings. This is another one where 99% of the time the defaults are fine, and then play around if you want, and it will spawn our particles on the surface of the mesh, like we can see here. The other cool thing that it can do, so we're actually just spawning single arrows, and with this mesh sampler, you can sample the color of the part of the mesh that you're on. So if you'll notice, the blue cylinder here is only spawning blue arrows, the red one spawning red, green is green. You get it. So you can do some fun stuff to match it and blend it in with that. I've seen people do that with like grass, so that the grass will kind of match the color of the ground it's spawning on. If it's dead grass, it'll be more yellow, all that good kind of stuff. Um, Next, we can have, it's talking about overwrites. So if we go to this spawner, this is specifically for the renderers in this case, but overwriting is kind of a generalized concept in that you can overwrite parameters. So uh, here, we're actually overwriting the position of, I believe it's in the bindings down here at the bottom of each renderer, we are telling it basically what do you want to listen to control your position, your color, your velocity, all that and so forth. So they have all of their defaults, and we can see because of this arrow, this is the only thing that's not set to the default. So if we revert it, it goes back to position is controlled by position. But in the stack, we have this. We're setting this thing called the particles render offset. So if we go back to particles render offset, you'll notice now we have the arrows and the spheres and the fluffies are at the same position. But if I set it back to render offset, they're now no longer in the same position. And that's just being done by taking its current position and moving it up 20 units. So you'll notice that the green spheres are always 20 units above wherever the base of the arrow is. So yeah, bindings are something that you can override, and that can be useful in a lot of different ways. Next, we have visibility tags. It's rather similar to the last one in that you can have multiple renderers set up, and use the visibility tag to control which renderer it should actually be using. So if we hide this other renderer, we can see that this one is spawning particles, and it randomly picks a renderer to use. This is done so on the particle spawn, it's exactly what it sounds like. So we have the tag that we are setting called the visibility tag, and we're saying we want you to be set to a value between 0 and 3 as an integer. And then on each of these renderers, we its renderer visibility is set to a certain one. So the first mesh one is set to 0. This one's to 1, 2, and then sprite render is set to 3. We can also change this over time. So this one's animated visibility. So you can see that in this one, the particles are actually just popping between which renderer they're using. So this one is, so instead of doing it on particle spawn, on particle update, it is switching through the 4 settings that it has to go through the 4 renderers that we have set up. The next one is texture sampling. This one's always very fun. So if we open this, we can see that it is sampling a texture with a bunch of particles. The way this is done, so we have a module in emitter update called spawn particles and grid. So we're spawning a grid of particles that's 256 by 256. And then we have a pre-built node called grid location. So this is used to determine where in the grid each particle is and assign that a value in both an x and a y axis. And this is done just like how we have UVs, so that you can use that value to sample a texture, which is the very next one. So we have sample texture. We're giving it, this is the image I want you to sample. I can change this to physics asset and it will sample that texture instead. And we can see the parameter that we set here is called the normalized array location. So just a fancy way of saying in this grid, up here will be 0, 0, and a value of 0, 0. And then the particle in the far bottom right corner will have a value of 1, 1. And we can use that to sample textures. Yeah. Last room, we have audio. I have had the audio off the whole time because you can actually hear this playing. But it's pretty simple. Basically, you audio is a thing that we can have particles do. So we can have them play audio when they die. We can have them play an audio when they hit things, so they can make actual, like clink sounds if you have a debris particle system, for example, so they can actually make sound. And then you can also just have the particles be playing sound as they exist. I've seen that where you can do that for Firefly. There was a Firefly system, so like the flies would blink in and out, and they would have a light on them that would blink in and out, and they would make a gentle little buzzing noise as they fly around, and then as they go away, they stop playing sound. Right? It's pretty similar to the other events that we've had. So you can have a play audio. By default, it just play. If you just do a play audio module on it and don't add anything else to it, it will just play this audio when it dies. You can also have play audio on collision, which is what this one's talking about. So we have to actually have collisions enabled, a collision module, and then play audio. And we're telling it play audio trigger is the collision and then valid collisions. So when a valid collision happens, play the audio. So yeah. This is a bit more abstract, but it's just talking about how you can sometimes not actually spawn multiple particles and kind of use the emitter as what you're using. The example this uses is that this is how some advanced water is done, where the entire surface of the water is actually just one big particle using that same sample texture method that we looked at a couple exhibits ago, where you only have one particle, it's cheaper. This is pretty rare to use, but it's good to know that it exists and it's an option. So yeah, and then recommend reading this if you get into more advanced stuff. And then lastly, we're going to talk about rotational force. So Obviously, the s- sprite renderers don't care about this as much. This is much more for mesh renderers. And I'll actually turn off two of these so we can see what it's talking about. This is mostly talking about rotation, and there are two main ways of doing that. We can just set rotation, which is what this emitter is showing off. So each particle just rotates a certain number of degrees every second. That's done here, mass orientation with a set rotational rate. So we're rotating around this vector with a rate of this. So I can change this to 10. They're all going to spin super fast, but they're all going to spin at the same rate, and it's not really dynamic. We're just statically setting it to be that. The other way we can do it is with some actual forces. So this one is uh, similar in that every single frame we are adding a force to it. So imagine you are in space and you have a thruster, right? And what we're doing is that we're telling it the thruster has a certain value, and you should calculate how much that changes its spins based on its mass. And we're determining the mass based on how big it is. So ideally, a big model or a big mesh should have a lot more mass, so the same sized thruster won't get it to spin very quickly. But a really tiny thing, if you stick a thruster on a basketball, it'll end up spinning very, very quickly. So the way that's done. So we have to first calculate its mass. So nice built-in one. It'll calculate its size and rotational inertia based off of its mass. And then down here, we have a mesh rotational force. And then, so it's saying we're going to add this much force to it. But again, this is an actual force instead of a determined rotational rate. So the small meshes spin much faster, and the big ones don't get spinning quite as fast. Um, and then, as with all of the other stuff that has any type of force or simulation, we can have drag, we can have a solver, all that good stuff. And then the final one is pretty close to the one we just looked at, but instead of a uh, thruster on an object that's adding force every frame, this one is it adds a kick at the beginning and then just lets it kind of deal with what it has. This is the same thing. So the size of the object depends how much it starts spinning based off of the same kick. If you kick a soccer ball, it'll go really fast. But if you kick a bowling ball, it has more mass, so it won't really end up moving as quickly, even though you added the same amount of force initially. So uh, very close to it. So we have the same where we're calculating the mass, uh, and we are adding a rotational force at the beginning this time instead of during. It's the same thing. So this is an update up here, but in this one, it's in particle spawn. So we're only adding it once at the very beginning. And then same kind of thing. We have a solver. Um, I don't actually know what this is here for. So it's just a bit more accurate way of calculating the physics of objects. So yeah, so we can have a lot of force at the beginning and drag it down. This one is adding an invisible thruster to each object, and this one is setting as a hard number. This is how fast I want everything to rotate, and it's not dynamic. So that is the end of the Niagara Particles Hall. Thank you so much for watching. And then if you want to learn more about Niagara, there are other videos about the other Niagara Halls or just any other parts of Unreal. So thank you so much.